Okay, in this video we're going to look at two examples of limits involving trig functions, and here's the first one right here. And if you watched the previous couple of videos, we looked very specifically at this limit and this limit, and we're just going to assume at this point that we know these to be true, whether you prove them or whether you looked at this function on a graph and evaluated it graphically, or perhaps you did it numerically. We're just going to assume at this point that we know this to be true, as well as this limit as well. Okay, so looking at this problem right here, we'll notice that we have a cosine up top, a tangent, and then this x down below, preventing us from directly plugging 0 in and evaluating it. So if we get an indeterminate form like we do in this case, we get 0 in the numerator if we plug 0 in. We get 0 in the denominator. Anytime we get an indeterminate form like this, we have to manipulate the function, change its close, if you will, so that it is effectively the same function, but it looks slightly different so that we can actually use direct substitution, or in this case, use one of these limits over here. Okay, so let's go ahead and get started. Let's see what we can do to manipulate this to get us a little bit better function to work with. Okay, I'm going to rewrite the limit as x goes to 0. And anytime I'm dealing with a trig function, if I don't know what to do, if I'm just kind of at a loss as to what to do, I turn everything into sines and cosines, and sometimes good things happen when we do this. This is multiplication here. So one technique for manipulating trig functions is just turn everything into sines and cosines. Okay, if we do this, I suppose if you need to put a 1 under here, that's okay, you can do that. Now you'll notice that in the numerator that this cosine here reduces with this cosine here. And the only thing left over now in the numerator is a sine. So now we have the limit as x goes to 0 of the sine of x. This is the thing that's left over after reducing our cosines. And then in the denominator, I'm left with just 1. Now this looks familiar. This looks like what we already knew to begin with. So we don't have to do anything more. We know that that limit is equal to 1. And you're done. Okay, the next function, or the next limit, is slightly more complicated. It might look easier than the first one. You might think that this takes on this form right here. You might be tempted to say that this equals 1, and you need to be careful, okay? Because if you look carefully at this form, one thing you'll notice is that this variable, and this variable are all the same. In other words, the thing that you're taking the sign of is the same thing as this that you're dividing by, and the same thing that you're letting approach 0. Well, this is the same as that. That's good, but what you'll notice is that the thing you're taking the sign of is not theta, but rather 5 times theta. Okay, life would be really good if there were a 5 there. Okay, well, you just can't write a 5. You just can't multiply the denominator by 5. What we've done is we've just changed really the value of this function. Okay, we effectively multiplied it by 1/5. But if I multiply the top by 5 as well, then really what I've done is I've multiplied this whole function by a disguised form of 1. Okay, so really I have this new limit statement. I have the limit as theta goes to 0 of 5 times the sine of 5 theta over 5 theta. I've just written this differently so that this kind of stands out a little bit. Okay, well, in prior examples we learned that evaluating a limit of a product of two functions, okay, and really this is just a constant, so you can use some other properties and just pull that constant out. Or you could just remember that taking the limit of a constant is just the constant itself. So really, I have 5 times the limit of theta as theta goes to 0 of the sine of 5 theta over 5 theta. Okay, so all I did here was recognize that the limit of theta going as theta goes to 0 of 5 is just 5. So I know this part of the limit is just going to be 5, so I pulled him out, and now I have this left to deal with. Okay, so again, you might be tempted to just jump right to this equaling 1, and it turns out that it's going to, but we need to see why. This isn't the exact same form as this guy is right here. Notice that this is the same as this is the same as this. And this is more of an academic step than a needed one. You just have to recognize that theta going to 0, if we let's just let y equal 5 theta. Okay, if we let y equal to 5 theta, I want you to recognize that theta going to 0, which comes from our original part of the problem, this is going to happen if and only if 5 theta goes to 0. Okay, or y. This right here, remember, is just y. Okay, but can you see that if theta goes to 0, that implies that 5 theta has to go to 0. Okay, if this variable right here is getting really close to 0, then the whole thing is getting close to 0. It goes the other way around as well. If 5 theta is getting close to 0, the only way that's possible is if theta is going to 0. So theta going to 0 implies y going to 0, and y going to 0 implies theta going to 0. So actually, I can rewrite this limit statement now as the following. 5 times the limit as y goes to 0 of the sine of y over y. Now this takes on the form that we recognize. Okay, so if you just evaluated this to be 1 from here, you would have been correct. But I fear that if we miss a step and we don't see really why this equals 1, I think that's an important exercise to do at least one time. Okay, so really what this is then is we have 5 times 1, and the whole thing is equal to 5. Okay, there you go. Once again, we had the 2 examples. The first one, we just used some trig identities to manipulate the function to get it to a limit of a function that we already knew. And the second example, we had to be a little bit more creative to introduce something to change our function to a form that we already knew. I hope that made sense. We'll see you around.